Welcome to the Chemistry 450 Atomic and Molecular Clusters video series. In this video, I will discuss the Liquid Droplet Model. The Liquid Droplet Model, or LDM, is in essence an extension of the spherical cluster approximation, wherein metal clusters are treated as classical, uniform conducting spheres. This approach allows us to relate cluster properties such as ionization energy and electron affinity to bulk properties like work function via the introduction of scaling laws. In general, we find that the predictions of the LDM improve as cluster size increases. This can be rationalized by the fact that the SCA is better for larger clusters, and that cluster properties are better described by classical theory as they approach the bulk size regime. However, at small cluster sizes, deviations from the LDM predictions are common, and it is not unusual to observe interesting structures superimposed on top of the LDM trends. For example, a plot of sodium cluster ionization energies as a function of cluster size follows the general trend of the LDM, but there is a clear alternation in relative ionization energy for small clusters. This structure hints that quantum size effect may be important in determining cluster properties. Quantum size effects are also observed in plots of vertical electron detachment energy as a function of anionic cluster size. The oscillation in the vertical detachment energy plot for anionic gold clusters can be explained if we view the clusters as quantized molecular systems. Anionic gold clusters with an even number of atoms have an odd number of electrons, while those with an odd number of atoms have an even number of electrons. Consequently, to detach an electron from clusters with an odd value of n, additional energy must be supplied to overcome electron pairing energy. If we take a molecular view of cluster electronic structure and assume Koopman's theorem, we see the ionization energies tell us how much energy is required to remove an electron from the neutral cluster's highest occupied molecular orbital. Similarly, the vertical detachment energies tell us how much energy is required to remove an electron from the LUMO. Thus, we can interpret the difference between the ionization energy and vertical detachment energy as a measurement of the HOMO-LUMO gap. In plotting ionization energy and electron affinity simultaneously as a function of cluster size, we gain some insight as to the evolution of HOMO-LUMO gap. As cluster size increases, we can reinterpret the HOMO-LUMO gap as the band gap between the valence and conduction bands of the metal nanoparticle. This band gap narrows as particle size increases to the point where the valence and conduction bands overlap and the particle becomes a bulk conductor. Spectroscopic studies of small metal clusters confirm that their electronic structures consist of discrete quantum states. Furthermore, as cluster size increases, the structured electronic spectra of these species collapse into a single transition. However, rather than being associated with the HOMO-LUMO gap, this transition arises from surface plasmon excitation. Surface plasmon excitations are collective excitations of conduction electrons relative to the ionic core. This collective excitation of the electron gas arises due to strong electronic correlation. The LDM also predicts scaling laws for the frequency and line widths of plasmonic excitations. For example, the LDM predicts that plasmonic excitation in silver clusters occur to higher frequency of the plasmonic excitation in bulk silver, approaching the bulk limit as size increases. While the liquid droplet model provides a good qualitative description of size-dependent metal cluster properties, there are phenomena, particularly for small clusters, that the LDM cannot explain. The most obvious example of this is the LDM's failure to predict magic number clusters in metal cluster distributions. These deviations from the LDM arise due to cluster electronic structure, for which a quantum mechanical treatment is required. I will discuss this topic in an upcoming video. See you next time.